Thermal engineering. In this paper, we will go to discuss about that gas power cycles. The objectives of the thermal engineering to provide the fundamental understanding of the principles and applications of thermodynamics, heat transfer, fluid mechanics, and energy systems. An introduction of this subject. This deals with the study of heat energy and its conversion to mechanical energy, electrical and other forms. It involves the analysis, design, optimization of systems and process that involves the heat flow, energy conservation and temperature control. Thermal engineering plays a critical role in various industries such as power generation, refrigeration, automotive, aerospace, and even electronics industries. The key principles and concepts. First law of thermodynamics explains the conservation of energy, that is, energy cannot be created or destroyed, only transformed from one form of energy to another form of energy. The second law of thermodynamics explains about the heat energy naturally flows from hotter body to cooler body, and entropy of the isolated system tends to be increased over that period of time. And application of thermal engineering, the power plants. The thermal engineering principles are used to design steam and gas turbine and optimize the boiler efficiency and improve the waste heat recovery. Automotive engineering in cooling system in vehicles and exhaust heat recovery system, and aerospace heat management in spacecraft, jet engine, and high-speed engines. In electronics industry, managing heat dissipation in electronics components and computer processor and LEDs lights to ensure the optimal performance. Emerging trends in thermal engineering. So many research are going on this area. Renewable energy systems, solar thermal system, geothermal thermal power, bioenergy are gaining importance in the context of sustainable energy production. The government also so many steps are taken to develop the solar thermal system. The one of the company Tata Industry invests the around 100 crores in solar development systems. The geotechnology and nanotechnology use of nano materials to improve the heat transfer efficiency in thermal systems like cooling electronics or enhancing heat exchangers, energy storage. The development of thermal engineering storage systems such as phase change material to store the excess energy to later use. Thermal battery management system. Effective thermal management system of batteries, electric motors increasingly to ensure the performance and safety. The first unit we will go to discuss about that air standard cycle. The both the spark ignition and combustion ignition engines are air standard cycles. As soon for air is intaked and heat also intaked, that we will get the work output. Okay, next the heated air is go to the exhausted to the system. The assumption of the cycle is air is as an ideal cycle used as a working fluid in the cycle. The compression expansion process are isentropic. The system is closed. The cycle is complete thermodynamic cycle. The specific heat are assumed to be a constant for all the temperature. First, we will go to discuss about that Otto cycle. In the Otto cycle is the ideal standard cycle for spark ignition engine. It is invented by Nicholas Otto, 1876. Otto cycle consists of four processes: isentropic compression, constant volume heat addition, isentropic expansion, constant volume heat rejection. That is the starting process. The both the valves are closed. Intake system. In the inlet valve is open. The atmospheric air is entered to the combustion chamber through the inlet valve. The piston reach until piston reach PDC, the air enter into the combustion chamber. Second stroke, in the compression stroke, both the valves are closed. Piston moves from PDC to TDC. At the end of the compression stroke, ignition process takes place. The ignition started in the combustion takes place again, and pressure and temperatures are raised. Piston moves from TDC to PDC, that is called power stroke. After process of power stroke, piston moves from PDC to TDC. In the exhaust stroke takes place. The Pressure and velocity diagram. The stage 1 to 2 isentropic compression process. Here air fuel mixture is composed. In this stage volume is reduced, pressure and temperature is increased. The stage 2 to 3, that is constant volume heat addition process. Again here pressure and temperature is raised. 3 to 4, that is called expansion stroke. From in this stroke pressure is reduced, volume is increased. 4 to 1 constant volume heat rejection process. These are the four process. That is temperature and entropy diagram is there. In this process, in the 1 to 2, that is entropy is constant. The entire process so in PV and TS diagram. Net work done is equal to heat supply to heat rejection. The efficiency of the cycle is purely depends upon the compression ratio. The efficiency of the Otto cycle is the function of compression ratio. Okay, in the efficiency increases with compression ratio. Okay, higher compression ratio, the higher thermal efficiency. The cycle continues the integral effective combustion process amongst many engines because it provides an excellent power output. Next one, diesel engine. The diesel cycle is the ideal air standard cycle for combustion ignition engines. It is invented by Diesel, that is 1898. The diesel cycle consists of four processes, that is isotropic compression, constant pressure heat addition, isentropic expansion, constant volume heat rejection process. That is in compression process takes place, that is heat rejection process takes, and expansion process and constant volume heat rejection process. That is stage 1 to 2. In the first diagram shows that combustion process, that is 1 to 2. The second process 2 to 3, that is constant wall pressure heat addition process. Okay, next heat addition process. In this process piston moves to TDC to PDC, and expansion process also, that is heat constant heat addition. After that expansion process takes place. At last the 4 to 1 last stage is heat constant volume heat rejection process. Piston moves PDC to TDC. In this diesel cycle, okay, here the pressure and velocity diagram and temperature and entropy diagram shown that the 1 to 2 isentropic process. Here heat is added at constant pressure process. 3 to 4 isentropic expansion process. Here volume is reduced, volume is increased, pressure is reduced. 4 to 1, that is 4 to 1, that process is constant volume heat rejection. The TS diagram also shows the same processor, but 1 to 2, that is isentropic conversion. Here entropy is constant. 2 to 3, that here the process is that is pressure constant, and net work done, that is heat supplied to heat rejection, that is heat supplied constant pressure process, that is called Cp into T3 minus T2. The minus of constant heat rejection process Cv into T4 minus T1. The efficiency of the cycle, that is ratio between the work done to heat input. Here in the thermal engineering, the thermal efficiency of the diesel cycle, it is less than the Otto cycle. It is less than the Otto cycle. This is purely depends upon the compression ratio and cutoff ratio. Compression ratio and cutoff ratio, because the gamma value is constant. Next one, dual cycle. Dual cycle first process is 1 to 2, that is called compression process. During the process piston moves from PDC to TDC. Okay, next process constant volume heat addition process, and one more process, the constant pressure heat addition process. But that is the dual cycle is combination of the diesel and Otto cycle. And last one, that is expansion process, heat rejection at constant volume and constant rejection process. Okay, next one, that is the heat supplied, means heat supplied both Cv and both the constant pressure process and as well as constant volume process. Cv into T3 minus T2 plus Cp into T4 minus T3. heat rejection process Cv into T5 minus T1. The thermal efficiency of this cycle is, that is work, the ratio between the work done by heat input. The efficiency of the dual cycle is function of compression ratio, cutoff ratio and pressure ratio. For same compression and cutoff ratio, yes, pressure ratio is increased. So the thermal efficiency of the dual cycle is increases. The most of the modern diesel engines works based on the dual cycle. The outcome of the thermal engineering, the understanding applying the thermal engineering principles and heat transfer mechanism, and design and analysis of variety of thermal systems using computational and experimental tools for model and analysis the systems, and environmental impact and importance of the utilization availability of the thermal system design, and engineering solutions of both in thermal systems.